All right, this is problem 14-34E. It's on page 756. The air in a room has a dry bulb temperature of 80 degrees Fahrenheit. It has a wet bulb temperature of 65 degrees Fahrenheit, a pressure of 14.7 psia, and we're supposed to do the same thing we did in the last problem. We're supposed to determine the absolute or specific humidity, the relative humidity, and the dew point temperature. Now, I selected this one, like I said, to complement 32. This one's actually easier to go through, of course, the psychrometric chart, but we'll be able to use the saturation tables to work this one. So let's go to the psychrometric chart in the English appendices, and I think they buried it in the middle of the no, they didn't. It's at the end as well. Page 997. Now, since I worked problem 32 for you guys, how about if you do this one for me? And I'll see if I agree with the numbers you come up with. So you saw how I worked the last one. All I did was I used a piece of paper. And is this one square? Maybe my piece of paper is off, because this one doesn't seem square either. My piece of paper's off.
This one's the same way that I use this piece of paper.
Is yours square? No, it's off also? Okay. So let's see. So a dry bulb temperature of 80 degrees Fahrenheit, a wet bulb temperature of 65. It's interesting because the 65 line is almost just beneath the enthalpy line of 30 BTUs per pound of dry air. Okay. What, I don't care. You want to give me the absolute or the relative humidity first? Take your pick. I have my numbers for the first two. I guess I could get the dew point temperature while I'm at it. Okay. I know what numbers I think they are. What do you think? One thing that may help, you can just make a mark at the stake point once you find it. The intersection of the dry bulb and wet bulb temperatures. That might make it easier to use your piece of paper to pivot around and find all the pieces of information we need.
I think the saturation temperature is 56.5.
56.9, I think that's about what I got. And I think what you mean is the dew point temperature,
Yes.
not the saturation temperature.
Yep.
Yep. So the dew point temperature, you go over the saturation line and then go down, and it's more than 55. It's to the right of 55 a little bit. Yeah, so what did you say?
56.5.
56.5, I'll take it. Did everybody see how I got that? In my head, I thought about 57 degrees, so either one's okay. Maybe his eyeball's a little more calibrated than mine. What else? What's that?
0.095.
You mean 0.0095?
Yes.
Right? And that would be pound mass of water vapor per pound mass of air. Notice something different between this and the metric chart. In this chart, they just give you pound per pound rather than gram per kilogram and make you convert it. Okay.
And the relative humidity is 44.5.
I said 45%, so I'm just going to write that down. Does everybody see how we're getting 44.5, 45%? Okay. Now let's see if we can do the same thing with equations. So let's go to the summary equations, and I'll try to make this a little bit clearer. Let's see what we can use to make sense of it all. The equations are all pretty straightforward. Let's just jot them down. The relative humidity is the mass of the water vapor divided by the mass of air, which is equal to the partial pressure of the water vapor over the partial pressure of the air. That's just what it is. The specific humidity, or the absolute humidity, can be written in terms of, let's see, mass of water vapor over, and you know what, I made a mistake here. I was copying the wrong place. This is the mass of air at saturation. And it should be the pressure at saturation. I skipped down and was copying the wrong line, I'm sorry. This is, I actually wrote the absolute humidity. I should have had this. So let's see. So the mass of the water vapor divided by the mass of air, and it's equal to 0.622 times the partial pressure of the water vapor divided by, really this is the partial pressure of the air, but we take the total pressure minus the pressure of the water vapor. Now those two are the main two equations that we will use. However, there's one more thing that's important. The dew point temperature is the saturation temperature at the partial pressure of the water vapor. And this is the thing that throws students for a loop. Now that should be everything that we need, because we're not dealing with changes yet, so we don't need an energy balance. There's one more equation that we may want. The pressure, the total pressure is just the sum of the partial pressure of the water vapor in the air. Now there's actually another equation, there's two more equations. I don't see them back here, but we've already used them in an example problem. You may want to add these in the back of, of the chapter. They go like this. It's just the ideal gas law. The partial pressure of the air multiplied by the total volume that the stuff takes up is equal to the mass of the air times the gas constant of the air times the temperature. And the partial pressure of the water vapor times the volume of the container is the mass of the water vapor, gas constant of the water vapor, and temperature. Okay? So these two are pretty handy equations to know. Really, these two are where this came from. Well, no. Yeah, because we got the 0.622 in there. Okay, so really this is already assuming ideal gas behavior. So now let's go back and see if we can calculate these numbers and see what we come up with. All right, to get the dew point temperature, we're going to need the saturation temperature at the partial pressure. So we need to somehow come up with the partial pressure of the water vapor. Now notice that we already have, let's see, we've got the wet bulb temperature and the total temperature. And so we may need one more equation. Hang on. Where did they put that? There it is. That doesn't seem to be what I'm looking for. That's got to be it. Yeah, there we go. That should be it. All right. So we should be able to use the equation at the bottom of page 754. Let me jot it down, and then we'll see how to use it. Let's see, I'm running out of space here for the sake of the camera. Tell you what, we know we're looking for these. Let me move them up here. Omega, phi, and the dew point temperature. Okay, here's the equation that I want to use to solve this problem. Cp T2 minus T1 plus omega 2 HFG2 over HG1 less HF2. Now what is this? Well, this really is representing a saturation process where the air has been taken to saturation conditions. And that's really what this is, right? This is the temperature at saturation conditions. So go back to where we were talking about sling psychrometers in the chapter. And that's, let's see.
739.
Yeah, 739. This is where the equation was derived. Better yet, oh, I remember, we were talking about this in the slides. Go to page 737. Now, you can think of the sling psychrometer as this process, this adiabatic saturation process in figure 1411, because that's really what we're doing. In fact, the humidity of the air around the wet bulb is 100%, because the wet bulb temperature is no longer going down any farther. Okay? So here's one of our temperatures. In fact, basically, you can look at it like this. Let me draw the system that we have there in the figure. Here's the makeup water, although we're really not interested in that. This is state 1 and this is state 2 in reference to this equation. So what are the temperatures? Well, T1 is 80 degrees Fahrenheit. T2 is the wet bulb temperature, which is 65 degrees Fahrenheit. Okay? So that tells us T1 and T2. And then what? Well, we need the can't think of the name of this, HFG. It's the difference between the enthalpy at saturated vapor and liquid, but latent heat of vaporization, that's what I was looking for. Okay, we need the latent heat of vaporization at state 2, in other words, at temperature 2. We need the enthalpy of saturated vapor at state 1, in other words, at T1, and we need the enthalpy of saturated liquid at state 2. Does that make sense? So, HF2, go to the back of the book, go to the saturation tables, and look up the English units, okay? Look for 65 degrees Fahrenheit and tell me what HF is. Like I said, I chose this one because we should have nice round numbers where we won't have to interpolate, whereas in the metric problem we would have had to interpolate.
33.08.
How much?
33.08.
And that's HF, 65? Okay.
Right.
All right, now, while we're there, look up HFG for state 2. What do we have for that? Should be right next to it.
1056.5.
1056.5 BTUs per pound mass. Thank you. Now let's go look up the enthalpy at state 1 of saturated vapor. What do we get there?
No, wait.
Go ahead.
1090.
1096.1? Thanks. Well, look, now we've got everything we need except for one thing. We'll have to look up the heat capacity, but that's not too much of a problem. And by the way, is this the heat capacity of the water or the air? You don't know. Let's go find out. It should be the air. If you look in the equation, they were dealing with the enthalpy of the water and the enthalpy of the air. And if you look through this, you'll find that it's just the enthalpy of the air. Anyway, so since you didn't know that, go to the back of chapter 14 where the equation is given. You may want to make yourself a note on page 745 that the CP in the equation, it's the lower left-hand corner of the page. 745. CP in that equation, it's page 754. I said 745. Page 754, the CP in that equation is for air. Okay, that's the heat capacity of air. So looking that up is no big deal. It's 1.005. What about the absolute humidity at state 2? We don't know that, right? What do we know about state 2? What we know is that the humidity at state 2, the relative humidity, is 100%. That's what we really know, right? So we're not quite done. We can't just plug and chug yet. We need to calculate the absolute humidity in state 2 from the relative humidity. Do we have an equation to do that? Well, sure. There it is. Right. We know that this is going to just be 1. So all we need is the saturation pressure of the water. Well, where? Here. So while we were there looking up this wet bulb temperature, we should have also looked up the saturation. That's not going to fit. We should have also looked up the saturation pressure, okay, which is P sub G. Okay. So would you please look that up? Go back to where we were looking up 65 degrees Fahrenheit in the saturated tables, and now look up the saturation pressure of water at 65 degrees Fahrenheit. What do you find? I think we'll end up using these right now.
That's 30578.
30758
30578.
578. Trying to switch all my numbers around today. And that's kilopascals. Do you see what we've just done here is the opposite of this? If we know the dew point temperature, okay. Oh, PSIA, thank you. Almost messed up. Okay, so anyway, let's see. There's something I wanted to tell you. What was I going to, I don't know, I've lost it now. I was going to tell you something. Anyway, so let's go from here and calculate the absolute humidity at the exit. 0.622 times 1 times 0.30578 divided by the total pressure, which is 14.7 PSIA, minus 1 multiplied by 0.30578. Does that make sense to everybody? Okay, so please plug this into your calculator, and we'll then finally get the absolute humidity at the exit, or at the wet bulb side.
Zero point zero one three two.
0.0132, okay? Well, now that we've got that, we can calculate the absolute humidity of the original air, the original 80 degree Fahrenheit air. Let's see, we will end up using that. We've used this essentially, so let me get rid of that because we're going to need the space here in a minute. And let me move this down because we'll need it as well in just a moment. In fact, sorry, I should have planned this out a little bit better. I don't have space, and I don't want to erase the state information. I want to leave that alone at the dry bulb and wet bulb states. So now let's plug in the numbers. So the absolute humidity will be equal to the heat capacity of the air, 1.005 kilojoules per kilogram per Kelvin, multiplied by T2 minus T1. So let's see, that would be 65 minus 80, and Kelvin is fine, the difference is the same as in Celsius, plus the absolute humidity at state 2, which we had somewhere, here it is, 0.0132, times HFG at 2, which is 1056.5. You know what? This isn't going to work, is it? I'm trying to do it again. I need the heat capacity of air in English units, not metric. This is not Kelvin, this is degrees Fahrenheit. you guys are really checked out. You're just letting me do whatever I wish. What's the heat capacity of air? Anybody know? I think it's 0.24 if I remember right. 0.24 BTUs per pound mass per degree Fahrenheit. See how units saved me? Because I was looking at this and realized it's in BTUs per pound mass, and then realized I had done something wrong. I hope this is on the video. I think it is. And then for the denominator, well then I need Hg1, the enthalpy of saturated liquid here that we looked up, 1096.1 BTUs per pound mass. And then I need to subtract off HF2, minus 33.08 BTUs per pound mass. Of course, the BTUs per pound mass will cancel through. Let's see, that's an addition. And we will get humidity. Really, it's pounds of water over pounds of dry air, but actually, you know what? We've already got a place for this. So plug this into your calculator, please, and then I'll just write it down over here. And notice that this really is omega 1. It's really the absolute humidity at T1. I'm going to move these down while you're doing that because I need some more space. There. What kind of humidity should you get? Should it be a big number or a small number? It should be small. What humidity did we get at the exit over here? I just erased it, but I can write it down. We found that omega 2 was 0.0132. Would you expect omega 1 to be more or less than that? Less, right? Okay, so anyone have a number that's reasonable for omega 1?
0.0097.
Anyone second that? All right, so that makes sense. Now what did we get first off? I've erased it now. We got 0.0095, or no, we said 0.0975, didn't we? Something like it. 9.5. So this agrees really well, right? What we got from the chart and what we're getting from the equation agrees very well. That's good. How about the relative humidity? Well, now that we've got the absolute humidity, getting the relative humidity is actually straightforward. Go to page 754. You see this equation? It relates the relative and absolute humidities to one another. Okay. Well, that's nice. Are we going to use this PG in it? No. We are interested in state 1, so we better use PG1. You see how there's a saturation pressure at state 2, and there's a different saturation pressure at state 1? So go to the back of your book, look up 80 degrees Fahrenheit, and read off the saturation pressure. How much is it?
.5745.
50745?
Yes.
That's PSIA?
Yes.
Okay. So now we should be able to calculate the relative humidity. We plug in the absolute humidity, which we just found, 0.0097, multiplied by the total pressure, which is 14.7 PSIA, divide by 0.622, plus the absolute humidity. Which one? Well, the one at state 1, the one we're interested in, 0.0097, multiplied by the saturation pressure at 80 degrees Fahrenheit, 0.50745 PSIA. Okay, the PSIA go away, and we'll have something that is, again, dimensionless. So plug that into your calculator, please, and we'll see if we get, what did we get before, 45% or so? Or am I thinking of the last problem?
It was something like that.
I think it was about 45%. Metric problem was 60 some odd percent, I think. So anyone that has a number, please tell me what it may be.
393.
How much?
I got about 144.
144? That's about what we should get. So in other words, 44%. It's about what we read off of the chart. Okay. Anyone second that?
The answer?
Yeah.
Okay, all right. Because it's possible that I've made a mistake along the way, and I don't want to just come out and say it's close on the chart, and there's two mistakes. Two wrongs don't make it right. Okay. All right, now, we've got two answers. How are we going to get the dew point temperature? This one's a little more tricky, because it's not the wet bulb temperature, it's not the temperature here. The dew point temperature is a different temperature. And the key is that we have to know the partial pressure of the water vapor. But now that we know the relative humidity, we can calculate the partial pressure of the water vapor. Look, the partial pressure of the water vapor, by the way, what is the partial pressure of the water vapor at the exit? Can you just tell me what it is?
Would it be, 0.3057?
Exactly, it's 0.30578, right? That's the partial pressure because the air is saturated. At this point, it is not saturated. In fact, at this point, the relative humidity tells us how close it is to saturation, right? Where we're talking about this saturation. So all we have to do is multiply the relative humidity by the saturation pressure at state 1, and that will give us the partial pressure of the air at state 1. I'm sorry, partial pressure of the water vapor at state 1. So take 44% of 0.50745. What do you get? Sounds reasonable. Okay. Now that would be PSIA. So that's the pressure of the water vapor is exerting out of that 14.7 PSIA at the entrance. Okay, that's all well and good. How do we get the dew point temperature? Well, now what we need to do is say if there's this much water in the air, right, then at what temperature will it start to fall out? It'll start to fall out when this is the saturation pressure. So now, this is the PV that goes in here. Now we need to find a saturation temperature that goes with that saturation pressure. Okay? It's not the saturation pressure at state 1, it's the saturation pressure that would be if the temperature of the air from state 1 were cooled far enough so that the water vapor starts to condense out. So now let's go one more time to the saturation chart, and look for a saturation pressure of 0.223 PSIA. We'll have to interpolate, but it's Thanksgiving, so we're not going to do that. Okay. Now, let me ask you a question though. What two temperatures is the dew point temperature between?
55 and 60.
55 and 60, and which one is it closer to?
55.
55, and before we said this was what, about 57? Right? So that agrees fairly well. So let's just say we did the interpolation and it's 57 degrees Fahrenheit. Check it off. Okay. If you're watching this video as an example, you may want to perform the interpolation to make sure you know where this all comes from. But I think we're done with this. Any questions about this? No, please no questions. No. All right.